Welcome everyone to today's physics and mathematics session. I'm delighted to have you join me. Today, we're going to tackle a very practical and fundamental problem: calculating the magnetic field at the center of a solenoid. Understanding solenoids is crucial because they form the basis of many technologies, from simple electromagnets in relays to sophisticated MRI machines. Let's dive in. First, let's visualize our setup. Step 1. Describing the diagram. Imagine a cylindrical coil of wire. This is our solenoid. Current flows through the windings, creating a magnetic field. Inside the solenoid, especially near its center, the magnetic field lines are nearly uniform and run parallel to the axis of the cylinder. Outside, the field lines spread out. Our diagram would show this cylindrical coil, clearly indicating its length, its radius, the number of turns of wire, and the direction of the current flowing through it. We also sketch the magnetic field lines running through its core, showing their uniform nature. Step 2. Identifying key variables and constants. Let's list the information given in our problem. The length of the solenoid, L, is 20 centimeters, which will convert to 0.20 meters for consistency in SI units. The radius of the solenoid, R, is 1.4 centimeters, while the radius is given. You'll see it doesn't directly enter the ideal formula for the magnetic field at the center, but it's important for assessing if our approximation is valid. Number of turns in the coil, N, is 600 turns. The current flowing through the coil, I, is 4 amps. Finally, we need a fundamental constant, the permeability of free space, denoted as μ0. Its value is approximately 4 pi times 10 to the 7 Tesla meters per ampere. This constant tells us how easily a magnetic field can be established in a vacuum. Step 3. Writing down the relevant equations and principles. The principle governing the magnetic field produced by current-carrying wires is Ampere's law. For a long, ideal solenoid, Ampere's law simplifies beautifully. The magnetic field B, at its center, is given by the equation B equals μ0 times N over L. Let's break this down. B is the magnetic field strength, measured in Teslas. μ0 is the permeability of free space, as we just discussed. N over L represents the number of turns per unit length, often denoted by N. This term captures how densely packed the windings are. The more turns per meter, the stronger the field. I is the current flowing through the wire. A larger current produces a stronger magnetic field. This formula is a good approximation for the field at the center of a solenoid, provided its length is much greater than its radius, which is usually the case in practical applications like this. Step 4. Substituting known values and solving for the unknowns. Now, let's plug in our values and calculate B. First, let's calculate N, the turns per unit length. N equals N over L. 600 turns over 0.20 meters is 3,000 turns per meter. Now substitute N, μ0, and I into our main equation. B equals 4 pi times 10 to the 7 Tesla meters per ampere. 3,000 turns per meter times 4 amps. Let's multiply the numerical values. B equals 4 times pi times 3,000 times 4. B equals 4,000 pi times 10 to the 7. Calculating the value. B is approximately 4,000 times 3.1415 times 10 to the 7 Tesla. B is approximately 1,596.3 times 10 to the 7th Tesla. We can express this in millitesla for easier understanding. B is approximately 15.08 millitesla. Checking your answer for consistency and accuracy. The meters cancel out and the amperes cancel out, leaving us with Teslas, T, which is the correct unit for magnetic field strength. In terms of magnitude, 15 millitesla is a significant but reasonable magnetic field strength for a solenoid of these dimensions and current, comparable to a strong refrigerator magnet or fields used in some medical applications. The assumption of a long solenoid is well met here, as L, 20 centimeters, is about 14 times larger than R, 1.4 centimeters. So the formula provides a very good approximation for the field at the center. Step 6. Conclusion and real-world application. So, The magnetic field at the center of this solenoid is approximately 0.0151 teslas, or 15.1 milliteslas. This value is quite strong and demonstrates the effectiveness of solenoids in creating controlled magnetic environments. This principle is fundamental to how electromagnets work, enabling their use in diverse applications like magnetic levitation trains, magnetic resonance imaging, MRI scanners for medical diagnostics, and even in simple electrical relays that switch circuits. Step 7. Additional insights and considerations. It's important to remember that the formula B equals mu naught Ni is an idealization. It assumes an infinitely long solenoid and calculates the field exactly on its central axis. For real solenoids, the field near the ends is not uniform, it's weaker and spreads out. The radius r doesn't appear in the ideal formula for the field on the axis, but it certainly plays a role in the overall magnetic energy stored, the inductance of the coil, and how uniform the field is off-axis. For instance, if the solenoid were very wide, large r, compared to its length, the field at the center wouldn't be as uniform. Step 8. Final summary and key takeaways. In summary, we've seen that the magnetic field generated by a solenoid is directly proportional to the current flowing through it and the number of turns per unit length. This relationship, B equals mu naught times N over L times I, is a direct consequence of Ampere's law and provides a powerful tool for designing and understanding electromagnets. This problem beautifully connects the macroscopic observation of magnetic fields with the microscopic flow of charge, reinforcing a core concept in electromagnetism. Understanding how to calculate and manipulate magnetic fields is crucial not only for physics, but also for various engineering disciplines. Thank you so much for joining me today. I hope this session has been clear and helpful. Please do like this video, subscribe to the channel for more physics and maths content, and share it with anyone who might find it useful. Your questions and comments are always welcome below. And if you have a specific problem you'd like to see me solve in a future video, consider donating to the channel. Each month, I'll select a few donor-requested problems to tackle in their own dedicated session. See you next time.